Hello everyone, we're live, coming out live here. This is I'm sorry, I have to check out our classroom. So this is a live webinar focusing on your second project. So what I'm gonna pretty much do is I'm gonna go through the necessary implementations on neural networks today. Just a second, I'm accessing my. I have to access my Udacity environment. So we'll be going through the implementation of neural net for the problem we are solving. So let me make sure everybody online, everybody on our classroom gets the. Make sure everybody is available. Make sure everybody that's online can access our webinar. So what I'm going to do today is go through the second lesson, which is everything you need to do. It contains everything you need to do on your second project, which is an introduction to deep learning using PyTorch for that. I guess everybody already knows that PyTorch is a framework for implementing deep learning models. So it already includes some models that have been trained, have been found to be useful for classifying images. So okay, I believe we are ready to start sharing the screen. And yeah, let's pretty much get this going because I guess everybody who's about to come has come by now. So let's get this going. This is quite a long lesson, I believe. So, well, at least it can get long. I'm going to try to make it shorter, as short as possible for you, with the same content, of course. So, let me access the classroom. So I'm gonna go through this lesson. I'm gonna access Jupyter Notebook with almost everything. So this is transatlantic solution, I guess. Going through the exercises. So I'll go through the lessons. So this is pretty much a classification problem, a binary classification, where you have to classify either images of cats or dogs. On your project, you actually have 102 classes, which is 102 flowers. So let's start by importing everything. Everything is imported right now by now. And let's start by loading the data. Our data, as you guys know, is in a folder called cat dog data, it's separate in cat, in train and test. That's it. So as always, let's start by implementing some transforms. As you can see, you know what these numbers are doing. They are adjusting the images to be centered at 1, and varying from -1 to 1. So normalizing the numbers between -1 and 1 and centering them. That's why we're doing this. These numbers specifically, they have found to be the numbers for this data set, of course. So that's what I'm doing. I'm normalizing. You have to close this term. I'll close the transforms. So what I'm doing here, I'm doing random rotation and random resizing to get to the same the same size for each image, doing random result on flip, and I'm normalizing, of course, in transform to tensor on this line. The reason why we're doing random is because if you look at normal pictures of cats, see how in different sizes they come in different shapes, and this helps the neural network to normalize. Maybe what it would do is catch this picture, this central picture, and shift it up, upwards, because as you can see, this is a cat which falls up. So uh, if we train a neural net on a standard picture of cat like this one, which is a pretty specific position of a cat, maybe the neural net wouldn't be able to generalize later and wouldn't be able to classify images that come like this or these different images of cats. So that's why we're applying randomized transformations. So now we're gonna set the transformations for the test set. I hate to code live actually, because when you code live, it actually takes a lot of the time I had for doing something else, but I decided to do it live so I can go and explain. What I'm doing here is just resizing and to the same, so they have the same size that before the training set, but I'm not doing any randomization because I don't want to do. You don't want to do randomization on the train on the test set, because the test set is pretty much you have to classify the image the way it comes. It makes no sense to randomize it. It only makes sense to randomize on training because you're trying to achieve generalization when you're training, but it's not the same thing when you're actually predicting. So I'm going to do the same thing. I'm going to normalize the image. Let me copy and paste this. It's going to be much faster. And here we go. Normalizing, loading on a train loader and on a test loader. I'm choosing the batch size of 64, so 64 image for each batch. You can think of the batch size as a group of images. So I'm taking 64 images at a time. So I want to feed the neural network 64 images at a time. And the way we choose batch size, we use them by power of 2, because in that way the GPUs are able to parallelize better the training and the classification of these images. So that's why you choose batch size of 64 when the pass on 64. And you can think the other algorithms that you have learned so far has having a batch size of 1, where you take each sample, run through the model, and do some optimization to make the learning. This time we're moving 64 images at a time because it's much faster. If we had to do this one at a time, it would take forever to do anything. Let me check the classroom. Nope, it's nothing on our classroom. So pretty much what I'm doing, I'm done here. I'm sorry, there's of course I'm sorry. Random decided. And it's done. We have loaded, successfully loaded the data. When you are implementing this on your second project, it's gonna be pretty much the same thing. But then you're gonna have have a validation loader. And to the validation loader, you're gonna apply the same transformation you did right here, because it is pretty much a classification, not a training. And this type of transform you do to the training because it can generalize. That's why you do random. That's why you do. But in both cases, they need to have the same size in the end. So it's 224 by 224 images. So what I'm gonna do now is I'm gonna load a pre-trained network. And why am I loading a pre-trained network? Well, because a model. Why I'm loading a model? Why we're using these models? Because we are using a complete model, not just a classifier. So as you can see, you have this model, but you actually have more models. Like let's search for Python Arch models. You can get a list of all the models, touch vision models. As you can see, you have pretty much this bunch of these are models that have been developed and tested to image classification. This is a very common one, BGG16. As you can see, instantialized here. I'm actually using the DenseNet, and you can pretty much access the papers behind this. What is it? DenseNet. Here it is. So you can see the paper. This has been a model implemented by a few Chinese researchers that has been proved to perform really well. This is a state-of-the-art model, so it has been does pretty well on images. So what is a model? You can think of a model as in two ways. For example, has a mod as a some. It is composed of basically two main items. First, you have these layers that come and extract features. For example, extracting features like feet, like or paws or head or ears. These models extract features, and by the end, you pass features to a classifier. So these models have been found to be very useful feature extraction. So this part we're not going to change. We're going to actually utilize this part from these models and just change the classifier. That's why we are using a model, because we're not feeding the classifier a raw image. You're actually processing the image through all these layers. These are convolutional layers. They use something called convolutional neural networks. You can actually look for these things online if you want. They are a bit more advanced than this course is to provide, but Udacity actually has a pretty good video on the introduction on this convolutional neural networks. So this is what's there's but basically what you have to know about these convolutional neural networks is that they are designed to process images. So that's why you have a few of these layers. You have one block, 2 blocks, 3 blocks. They are used for extracting the features and passing good vector features to the classifier, which is going to be this guy here that we're going to replace. And the reason why we're going to replace, because when you load from Torch Vision here, this one is already trained, but it's not trained on our dataset. It's actually trained on this ImageNet dataset, which is, as you can see here, contains 1 million labeled images for 1,000 categories. But our data is different, so we're gonna just classify. But our data is different, but it has the same features like ears, head, and things like that. From that, this image, a few of them actually also share. So that's why you don't need to change the way we extract features, but you have to change the classifier itself. So I'm gonna load this, execute this line, and we actually gonna see the model. Sorry, let's see if the internet's working. It's working. I'm gonna stop the screen. I'm sorry, we are experiencing problems. Now we're loading, and we have loaded. With this line, you can look through our model. So what it has is this convolutional layers that we're not gonna touch these convolutional layers because they are doing just fine. They are extracting the data pretty fine. But by the end of it, we have the classifier, and we need to know how many inputs the classifier take, which is 1,024 inputs. So by the end of this, so by the end of this last convolutional layer, it's going to pass 1,024 a vector 1,024 features, which you can think of as a vector of numbers to this classifier, and that's why you need to have a classifier that takes 124, and it's not going to output 1,000. We're going to output 2 actually. So let's go ahead and change this classifier. I already did this here. So basically, what I'm doing, I'm taking 1,024, passing to 500, then going again and moving 500 to 2. And I'm going to change the classifier of the model of this line. That's what this line is doing. It's just, so pretty much by now what we're doing, we are actually using all these convolutional layers that these researchers thankfully implemented for us. They have been proven to work pretty well for extracting data and features from the images, and we are actually using them the way they come, so we don't need to change them. But we need to change our classifier because the classifier was trained for the ImageNet dataset. We have another dataset, so we're just going to change the classifier. And what we're doing here is we're not gonna update we're not gonna uh, train the train this train this layer. We're only gonna train your classifier. So that's why you're gonna looping through the parameters of the model and not requiring this setting this requires grad to false, because in this way it's not gonna train this model. And then we change for the classifier, but our classifier here is actually has this requires grad to true, so it will actually update as we train this. So let's execute this block of code, and done. We have frozen the parameters for all these layers, and then we change this layer, this classifier, to be our classifier. Then go from 1024, as this model actually say right here. And since we have two categories, which is cats and dogs, we are outputting 2. So in this part, you actually are free to go from how many to 1024 to maybe 600, 700 is your choice, and maybe put an additional layer here. That's your choice. This is the way I implemented this thing. So, and it has been proven to be working. So let's go ahead. And now we're gonna go to the CUDA tests. So when we say that we have this limited amount of time, here is because we are actually using a much more powerful environment to train this model, because it requires a GPU. And I hope everybody knows by now, but a GPU is something like this, which is graphic cards. And graphic cards are pretty awesome at training these models. So here we have an example of a 1080. So let me show you the 2080 Ti. This is a pretty expensive graphic cards. What is it? So it will cost up to $1,000, maybe more than $1,000. And we are not actually using a single one of these guys. We're actually using quite a few of these. They are on Udacity's infrastructure, but we are actually using more than one GPU. So that's why it would be very expensive for you to do this on your local machine, because you have to arrange yourself a GPU. So we're gonna do next is we're gonna compare how the model works differently, both on the CPU using your Core i5, Core i3, i7, what else? Basically your Intel or AMD CPU, and how it does using one of these guys, one GPU. For that, we're gonna finally enable the GPU. As you can see, I actually have a lot of time right now still, but I'm gonna enable this, and I'm actually using my time right now, so you have to be pretty fast. So as I said before you begin to training your model, you set up everything, and only then you activate the GPU workspace, because you don't actually need the GPU workspace for anything else, just for the training. And when you're ready to train your model, then you activate the GPU, so you won't be wasting your time, your precious time on your precious GPU time. So this is what I'm doing right now. I'm just wanna test how fast it goes, how faster it goes than a CPU. So here we go again, executing everything from the beginning. it actually takes a while, so we have to wait a little bit to test how. But you're gonna see that the GPU model actually runs in orders of magnitude faster. We're clocking this with the time library, but the GPU model actually run several orders of magnitude faster. So you're gonna see how slower it would be to implement this on the CPU and why you need a GPU. Actually, yeah, it takes a while. So basically, the time you're seeing why it takes so long is because I'm trying to run on a CPU for a little bit of time. So that's why you're gonna see it taking this while, which is a good thing for comparison. And you can actually write agnostic code because maybe you don't know if CUDA is available or not. If your workspace, maybe the computer you're trying to run has a comparable GPU or not. So that's why you write this code, because if it doesn't find the CUDA, it's gonna run on the CPU. See how long it took for the CPU. It took all this time for the CPU. It was pretty faster when you use CUDA. Let's keep our GPU workspace going, because I'm actually gonna do this right now. I'm gonna use it right now. So here we are implementing the model. We're gonna see how I implement how I am implementing one of these the training. So for the training, I'm actually not gonna do this by code. I'm gonna do this by a function. I'm gonna define a simple function that's gonna run all the training for us, and so we can just call this function later, and it's gonna be much more compact code. So let me define this function. You can call it however you like. I can call this deep learning, or I could also call this my deep learning or deep learning training. I'm actually going to call this deep learning training, because it does the training for us. So what this function is going to do is going to take the model that we define. It's going to take a train loader for loading or taking train data. So I'm going to call these parameters like train data. You can actually call the name doesn't interfere with anything. This is just a number that you call. You can actually call my model. Anything like that. It's just as you have been using Python. It's just a name for your parameters of function. So you can name it pretty much as much as you like, as long as it makes sense, of course. I'm gonna print every a few steps, because I'm not gonna leave it running without me knowing that the optimization criterion. Actually, I'm also gonna set the optimization criterion from outside of the function, so I can choose a different criterion if I like. I can actually play with this code by a while. And now what I'm gonna do, I'm gonna set up the device. It's gonna be this little guy here. So I want to set this device to use CUDA if I have CUDA available. If I'm running on a CUDA machine. But if I'm not running on a CUDA machine, I'm gonna set it to use CPU. I'm just gonna use the CPU. If I try to run it on CUDA and actually the computer does not have CUDA, the code's gonna crash, because it's gonna say that it did not find the necessary hardware. So keep that in mind. In Jeffrey, I'm taking these parameters and starting and using them right here. Equals. I'm gonna count the steps starting at 0. And I'm finally gonna change my model to the CUDA. This is the code to send the model to the device. I'm actually changing my model to whatever device I have available. And I'm gonna look through the epochs. I'm gonna compute the running loss. How much loss do I have? I'm gonna set it to 0 right at the beginning of each epoch. Now I'm gonna look through inputs and outputs, which takes the train data. This is actually should be a loader, a data loader from the PyTorch. This data loader that you define here, this train loader. So I'm gonna look through it. I'm gonna actually specify this here, the train loader equals whatever train data that I pass through this function is gonna be set up here, and I'm gonna look through this guy. And I'm gonna start counting my steps. This is the first step. Inputs. Also have to send. You also have to send the inputs and the labels to whatever device you're using. Hopefully, you're gonna use CUDA for training. So, but if you're trying to run this on a code that is not on a device that you don't know, you have to write this device agnostic code, so you won't crash if CUDA is not available. But fortunately, not every computer has a NVIDIA GPU, so I have to do this. And first, I'm gonna go to the forward pass. This is pretty much what you have been taught in through the PyTorch lesson. So I hope this is not news for anybody. I'm gonna do the forward passes, which is taking the output, passing everything forward, passing the inputs forward, and I'm getting the outputs, and then computing the loss. Whatever criterion I have to the output that I receive from my model against the true output, which is these labels that I have here. And I'm gonna do the backward pass, which is propagating the back propagating the error back to the neural net. And finally, I'm gonna sum all the error that I found through this process. And when I'm reach my steps I reach the same as I print every as I have defined. Uh, I'm gonna print. This is what this operator does. It divides this number by this number, and it gets the remainder of the division. So this remainder is 0. It means that I have come to print every, which means that I have come to whatever print every that I choose. So if I say that I want to print it every 40, so when each steps here gets to 40, is gonna print something. It's always good to print something to know that your model is running and you're not running any problem. It's just, and what I'm gonna print is gonna print my error. I'm gonna print what epoch am I in. So maybe I wanna do to 10 epochs or even more. So I wanna print which epoch I'm in and how many epochs I have actually have set up. And I'm actually gonna print the error, my loss. I'm gonna format this error so I don't have so many decimal cases. I just wanna few. I'm not gonna print the combined error. I'm just gonna print it divided by how many steps have I taken. So if I have taken I'm sorry, I have this parenthesis wrong here. So this is what I'm doing. And I actually don't need to. And I'm gonna once again I'm gonna set up the running loss to 0. So basically, what I'm doing, I'm summing all the losses and I'm dividing by how many steps have I taken. So I go 1 loop, 2 loops. Imagine that I have set up to 10, print average to each 10. So when I do 10 and I divide this by 10, so I get the average loss for each step. And I see how my model is improving. So this function does deep learning, and as you can see, compiled just fine. And I also have to check for the accuracy how my I'm gonna also define a function to check for my accuracy. It's pretty much pretty close to what we just had, so it's much simple, but it's much simpler. So once again, name it the for the name that you like. You pass a loader, so I'm gonna just pass a pass loader. You can actually name this parameter the way you like. So I'm doing the same thing, and I have to send to the CUDA. If I'm running my model on CUDA, if you're running your model on CUDA, you actually have to send everything to CUDA before. I'm going to see how many correct and how many predictions I'm doing, how many correct predictions I'm doing, how many predictions I'm doing, and I'm gonna do no grudge. There's no training here, just validation. So I want to have no grudge. I have to send everything to CUDA again. I'm sending my images to CUDA, and I'm sending my labels to CUDA too. And I'm gonna compute my outputs. I'm gonna pass the images to the neural net, and I have this. As you can see, I'm throwing my CUDA time away, but that's okay. I don't actually need as much time. Here I'm getting how many predictions did I get. So I'm gonna see how many correct predictions I got. So I'm gonna set it to equals to the where the prediction was equal to the label, and I'm summing the item, which is 1, and for each one that I get here, this a prediction that I did correctly. So this is what I'm doing. And in the end, I'm gonna print my accuracy as a percentage. Which is the correct predictions divided by the total predictions. So Oh, I'm sorry, I forgot the dots. So that's fine. Now I have both my training and my validation function. I can actually call them the way I want, but the way to call this is to call the function. I'm actually gonna call this function. The name of the model is just model. The training data is the train loader. How many epochs I can have? 10 epochs, which is a good number for. I have seen that it does a good. It is a good training time for getting at least 70% on your project. I'm gonna print at every maybe 4 steps. It's fine. I haven't defined the criterion yet, but defining a criterion is actually pretty easy. So I'm gonna use this loss, and my optimizer is gonna be I'm gonna define a learning rate, which is pretty small number, so this is fine for me. You can actually play with this later. And my optimizer here is gonna be I'm actually gonna call this my criterion. And after I do the training, I'm gonna do the I'm gonna check the accuracy. I can do this on another cell actually. I'm gonna use this same cell. It's gonna print a lot of things, and I don't wanna to mess up my printing. I wanna know well, but and how did I call my loading data? Test loader. So this is how I check for my accuracy. And if I run this code, I'm gonna train the model, then I run this code, and I'm gonna check for the accuracy. But I'm not gonna do this right now because this takes quite a while. This will take more than an hour to do. This data set actually is pretty big. It's much bigger than the one you have on your for your training. I'm using the DanceNet. I actually should suggest you to start by using this BGGNet, this model here. So it will give you a pretty nice, some pretty nice accuracy. I have tried this BGGNet, but I'm not gonna do this because it's gonna take a while. But what I am going to do is because I have already trained a model beforehand because I actually had it saved, but I'm gonna show you how to save it. I'm gonna have this guy here, class 2 AGX, which you get from from a folder. Get this from a folder. So this string data actually comes from this folder here that I have defined way back there. Comes from this object, And you can do torch.save. This is how you save a checkpoint of your model. If you wanna come back to it later and train it, you can do so. So I'm gonna actually save how many epochs I. It is a good idea to use the epochs defined here. Because I can save it much easier later. So I'm gonna save the epochs. You actually glad to define how these keys are named, but then you're gonna have to remember how you name these keys to load it. Now I'm gonna save my parameters, how my neural network got adjusted by the end of the training. And to do that, you name this guy. You get a state dict. The model from your model, you got the stage dict. And I'm also gonna save the stage of the optimizer, which is useful if I wanna to keep training it later. And I'm gonna have to pass in a number, a name. I'm just gonna call this the checkpoint. I'm gonna call it the checkpoint of my model. So now if I run this code, I'm gonna save this my neural net to my disk, and I can load it later. You're gonna see it's gonna create quite a huge file. The file has maybe over 1 gigabyte, which is pretty big. So I'm not going to run this code, and the reason why I'm not going to run this code is because I have already done that before this class, so we wouldn't waste time training, because the training for one single epoch is going to take you for about an hour. So be mindful of that when you're training your model. So I'm not going to do the training, but I'm going to load the model. On my model, I'm going to use my previous model. Actually, when you load a model, it has to have the same structure that your previous model. So I have done a model just like this, using the same DenseNet and the same classifier. And I did the training on this classifier, saved to the disk, and now I can load this. And this shows you how to load the classifier. I have to load the checkpoint. I'm gonna call this my checkpoint. Once again, you're free to call this however you like. And I'm getting the checkpoint, and I'm gonna use my model to load the parameters that I have optimized. And this is going to be my checkpoint. And as I named it the same, gave it the same name as I did here, I'm gonna access this key. And I got an error. Oh, I'm sorry. I actually had named it, gave it a different name. I can actually go outside and look. So let's see how I name it my PTH file. I named it model checkpoint. So this is how I should call it. Let's see if I'm throwing this error. Yeah, I believe my model is not saved. Nice. Yes, it did not save my model because as you can see, it is only 31.4 megabytes. Model is actually much bigger. I'm gonna show you right now how bigger a model actually is. And I'm gonna finish this. Actually, from here we're fine. This is, I believe, this is all you have to do in your internet. The reason why I did not save is because this is there's some limitation for you touch on this open on my end of the machine because they don't won't let me save a lot of a file that's so big as 1 gigabyte or 2 gigabytes maybe. So what I'm going to show you is when I implement this project by myself, and I'm going to show you how I did that and how it does works just fine. So let me go to the project, my project itself. And I'm gonna enable the GPU once again. I'm not gonna do the deep learning, but I am gonna load the, where's the loader? Which is here. Actually, it should be down. As I saved it, I can. Why you not? Apparently, they erased my file as well. It's not on my, so that's why I cannot load because they erased my, because it's such a big file, so they erased my file, the file that I saved. But that's not too much of a big deal. I have shown you how to load, and this is how you save. This is how you load. This is how you save. This is how you load. So I hope you guys can continue your work from here. And this is all we have time for today. Thank you so much for watching. Any problem, I'm always available. I'm finishing this webinar right now, as he has already went